So today we want to look at a few examples to really nail this down, okay? And make sure that we understand how to, first of all, set up the equations using related rates, and then how to solve for what we're looking for, okay? So let's read through this example here. It says, an airplane is flying at an altitude of 6 miles, S miles from the station. Please be careful to read the problem carefully and also to look at the diagram that you're given carefully. All right, most of these problems, we will give you a picture to go along with it. The reason why I say that here is because S miles from the station, some people might think, okay, well, is that from where they're at along the ground, or is that in a straight line? And here the diagram clarifies that for us. S is in a straight line from the airplane to where this little radar station is, okay? So what we want to figure out, we have this diagram, and one of the things we need to figure out is what are the variables in the problem and what are the constants, if any, okay? And you'll notice in the diagram here they do label the 6 miles as 6 miles. We didn't use a different variable for that. And the reason for that is because our plane is flying horizontally. It's saying that it's flying at an altitude of 6 miles. So that is not changing. The plane's not going up or down or anything like that. It's just flying 6 miles off the ground. Okay? That makes a big difference. Because remember, we're going to be taking derivatives. If it's a constant, when we take the derivative, it's going to be 0. If it's not supposed to be a constant and we plug a number in and then take the derivative, we're going to be losing things. Okay? So, if we read the rest of the problem here, it says, an airplane is flying on a flight path that will take it directly over a radar tracking station, as shown in this figure. If S is decreasing at a rate of 400 miles per hour when S equals 10, what is the speed of the plane? Okay, so here we have a particular speed that S is decreasing at a particular moment when S is 10. I'm not going to plug the 10 in until later after I have taken the derivative. Okay? Now, the first thing we need to do is identify what we're given and what we're trying to find. All right, so we are given S is decreasing at a rate of 400 miles an hour. That's ds dt. Okay, anytime you hear a rate, it's something dt. So here, ds dt. And what value are we going to give to that? Very good, Michael. Negative 400. Why are we putting negative 400 miles per hour? Yeah, it's decreasing, okay?
But when you calculate it,
If I made it positive 400, that would be like the distance, it was getting further away and it was increasing, okay? So it's very important that you get these signs proper, correct, okay? Now, we're asked for the speed of the plane. The speed of the plane.
Velocity. So it's going to be the derivative of position.
Okay. The plane is flying this way, right?
Over time. So.
What?
dx dt.
Yeah. This is the same as the x is going to be. It's just drawn, these are parallel. Okay, we could have drawn it up here or down along the ground. Either way, we're looking for the change in our position over time. That's dx dt. All right? Now,
X is the speed.
X is how far away along the ground the airplane is from the radar station. Okay? So how fast the plane is going is going to be dx dt. All right? So then we have, then we need an equation. What equation are we going to use in order to relate these variables together? Yeah, good, the Pythagorean theorem. Okay, x squared plus 6 squared is going to equal s squared. All right, s is our hypotenuse, so we've got that. Notice I plugged in 6 because it's not changing the whole time, so I can put the constant in right now. I'm not putting in the 10 yet because that's just one specific moment. So now I take the derivative. I have 2x dx dt plus 0 equals 2s ds dt. Alright, so let's plug in what we know. We know that s is 10, so it's 2 times 10.
X is 10. What S is 10?
S is 10, yeah. And ds dt we know is negative 400. Okay? The challenge here though is we have two other unknowns. I know I'm going to be looking for dx dt, but in order to find that I got to know what x is.
X equals 10 miles, isn't it?
No, s is 10 miles. What's x going to be?
8.
You can find the
Wait, what?
8.
8. How'd you get that, Glow?
The first one, x squared plus 6 squared.
Yeah. Here's where, if you're missing a part, we're missing the x, we can look at this specific moment with the formula that we had. Okay? X squared plus 6 squared is 10 squared.
Why do you know 10?
S is 10, we were given that.
Oh.
Okay? And as a result, you solve this and you get x equals 8. Okay? Or if you recognize a 3, 4, 5 Pythagorean triple, 6, 8, 10 is our triple here. So now I know x is 8 and I can actually solve this, and I get dx dt equals a negative 8,000 over 16. Yeah, negative 500. And by the way, what's my unit of measure? It's negative 500 miles per hour. Now that's a vector quantity. The negative tells us which that it's decreasing. Okay? Yeah, so if we want speed, the speed then would be really the absolute value of this. So it's 500 miles per hour, and it's decreasing, we could say, but that's the speed. Okay? Okay, so there's our answer. Decreasing at 500 miles per hour. Yeah, here, the negative, guys, is simply telling us that we're going towards the station, so x is decreasing. How fast is it decreasing? 500 miles an hour.
So that's the deceleration. So 500 miles per hour is.
It's not acceleration. We'd have to do a second derivative in order to do a acceleration aspect here.
So what
But
does it tell us? So what is 500 then? Is it the speed?
500 is the speed. It's how fast we are moving in this direction.
When s equals 10.
Yeah, as opposed to a positive 500 would mean we're going 500 miles an hour the opposite direction.
Okay.
Okay? Yes?
So to do this, you just took the derivative of the Pythagorean theorem?
Yeah, that's all we did. So let's check out another one. This one is kind of an interesting one because initially you look at it and you see a right triangle, so you automatically think what?
Pythagorean theorem.
Probably Pythagorean theorem. However, let's read this one a little more carefully. This one has a number of different elements to it that you've got to be able to figure out. It says a TV camera at ground level is filming the liftoff of a space shuttle. The space shuttle is rising vertically according to the position equation s equals 50t squared. So this equals 50t squared.
Why the height?
Yeah, that's how high the space shuttle is off the ground at any given time. Okay? Now they're telling us S is measured in feet, T is measured in seconds. And it says the camera is 2,000 feet away from the launch pad. Okay? Now, is the camera moving?
No.
No, so that 2,000 is a constant in this problem. Alright? So, notice here, we don't care about how much this is changing or the speed of that. What we care about is the rate of change in the angle of elevation of the camera. So like if we were programming this camera to follow the space shuttle up, and we knew how fast it was going to be increasing, we could then program it using a rate of change for our angle. How fast should our camera tilt up? Because I don't know about you, I wouldn't want to be standing only 2,000 feet away from a space shuttle that was launching. Might get a little hot. So we're going to look at the change in the angle of elevation. So you'll notice here in the diagram, this is our angle of elevation. If we have the camera looking up at the space shuttle, it's the angle between the horizontal and our line of sight. So there's our theta. Theta is that angle right there. So what are we actually looking for in this problem?
D theta dt.
Yes, it's the rate of change of the angle with respect to time. D theta dt. Okay? This is one of those ones where you might be stuck for a while if you don't really connect what you're looking for to this derivative notation. Okay? We're looking for d theta dt. And we're looking for it when t equals 10 seconds. Alright? So this is why we're not going to end up using the Pythagorean theorem because that doesn't have a theta in it. But we do have a right triangle.
We can use cosine.
We could, well, let's use tangent. Okay? Yeah, we'll use tangent here. And tangent of theta is going to equal opposite S over adjacent, 2,000.
Wait, isn't it S equal to 50 t
Yeah.
squared?
It is, okay? So this is an extra element here. Yeah, we're going to substitute that 50t squared in for S. Alright? If we didn't, we'd have to go back and figure out what ds dt was and do some other substitution later. So we'll substitute now instead and make things a little bit easier on ourselves. So 50t squared over 2,000 is tangent of theta.
It's gonna be t squared over.
400.
T squared over, what is it, 440? Okay, so that's tangent of theta. And guys, the more you simplify and stuff here, the easier your derivative will end up being.
Don't you plug
Okay.
in 10?
5 over 2.
You didn't take
When do we plug in 10 here, guys? There we go, after we take the derivative. So let's go ahead and do the derivative next. Well, the easy side's the right side, so that's just going to be 2t over 40, which is t over 20. Okay, so we're taking the derivative with respect to t. What's the derivative of tangent theta with respect to t?
Secant squared theta t d theta over dt.
Yes, there we go. We pieced it together there, okay? Secant squared of theta, that's the derivative of tangent, times d theta dt.
How did you went from t squared over 40 to t over 20?
The derivative would be 2t over 40,
Mm-hmm.
so I just reduced the
yeah.
2 over 40.
Wait.
Okay.
So now we just have to. Oh, it's not gonna help.
Well, what do we have to do? Because right now, we're a little bit stuck. We can plug in the 10 for t,
I mean, yes.
but what's theta?
Yes, that.
What's theta?
Can you
the
plug in?
inverse tangent of 100 over 40. That's
Um,
the point when t equals 10.
Okay, So yeah, that's where we're getting, actually, not just 100 over, wait, oh yeah, yeah. If we go back a step, because at this point, we're kind of stuck if we don't know theta. If we go back a step, and you can go back as far as you want, it doesn't matter which of those previous equations you use. Tangent of theta is t squared over 40. Well, if t is 100, then tangent of theta is going to be 100 over 40. If t is 10, we have 100 over 40. Okay, so now we're using our calculator and just figuring out what the inverse tangent is in radians. Always do it in radians.
Why didn't we do that from the beginning?
We could have at the very beginning, but we didn't necessarily know we needed it until now. Oh, we could have done it, yeah. But now that we get to this point and we're a little bit stuck because we have the 10 over 20, but we don't know what theta is. 1.19 or 91? Okay. I couldn't remember. 19, and let me get rid of the extra one there. There we go. Okay, so theta is 1.19, and so now I know I have to take the secant squared of 1.19. So your calculator doesn't necessarily have a secant button, so you just have to do cosine and square it and then do 1 over that. And you get what, 7.25? Is that right? Come on guys, you guys are the ones sitting there with a calculator. Some of you get to a quiz and you have no idea how to use your calculator because you're not following along. What is it? 7.24? 7.24?
Yeah.
Okay.
Yes.
And that equals 1/2. So now d theta dt is going to be, I divide by 7.24.
0.069.
0.069.
Yeah.
Okay. And it's going to be that. Now, units of measure are important on this to make sure your answer makes sense to someone looking at it.
Radians per second.
Very good, Misha. It's radians, because that's what we're measuring the angle in. It's radians per second. If you're not sure, look at your derivative. D theta, theta is in radians. dt, t is in seconds. So it's got to be radians per second. Okay? So now I want to look at this problem. This is a very different kind of one, but it kind of shows us the inner workings of one of the cylinders of your engine in your car or any kind of internal combustion engine that has cylinders. Just to kind of give you a little glimpse inside here. Alright, you've got the spark plug right here that's connected to your battery. And these are little fuel injectors that spit gasoline into this compartment here. And then when the spark plug sparks, it creates an explosion. That's why it's called internal combustion. Alright? That explosion pushes this piston back and forth like this. And the reason why it comes back is because of this arm right here. As this gets pushed, this arm rotates, and the momentum it creates pushes this back. Okay, so, and then it explodes again, and it shoves it back, and the momentum carries it back in, and if everything is timed properly, then as this piston is approaching here, there's another explosion that shoves it back. So that's how an engine works. Okay? Now, in order to time it properly, the computer in the car has to be programmed right. Or before the cars were run by computers, they had to have the mechanics exactly right so that the timing would be perfect. So we have a situation like this. This little arm is 3 inches long, and the arm that connects from this joint to the piston is 7 inches long. This distance here between this pivot point and this, where it connects to the cylinder, is going to vary depending on where along this shaft the piston is. Okay? So we're thinking about this here, and now that we kind of understand the diagram, let's think about what's going on here. It says that in the engine shown, a 7-inch connecting rod is fastened to a crank of radius 3 inches. The crank shaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of the piston when theta equals pi over 3. Alright, so this one we've got to make sure that we understand what's going on. Theta is that angle. The velocity of the piston, what are we really trying to find here? dx dt. dx dt. Alright, dx dt is going to tell us, because that is modeling the motion of this piston back and forth, okay? The piston is going back and forth that way, so x is getting longer or shorter, longer or shorter. Okay?
But the rate is going to be different all the time. It's going to be like a sine wave.
I'm sorry, what?
The rate of the motion will be different all the time. Because it will eventually stop and then go.
You're right, it will. That's why we need to figure this out.
It's like a sine graph.
It is. We're actually going to use a trig function here. Okay? Now, one thing that we have to translate a little bit here is the crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute.
So that's the derivative of
That's d what?
Oh wait, yeah, d theta.
What'd you say? d theta dt. Now, hang on, because we're not quite done here. D theta dt is 200 revolutions per minute, RPMs. Actually, if you think about angles in standard position, they rotate counterclockwise naturally. So that's okay. But think about it here, revolutions, that's not a unit of measure really that we use for angles. So what do we have to convert that to?
To radians.
To radians. So if I'm doing 200 revolutions, how many radians make a revolution?
2 pi.
2 pi.
So it's multiplied by 2 pi.
400.
So 400 pi
Oh, that's many.
radians per minute. One full revolution in radians is 2 pi. So if I'm doing 200 of those, I'm passing through an angle of 400 pi radians every minute. Okay? So that is my d theta dt. Now,
There are engines that do 800 revolutions per minute. 8,000.
8,000, yeah. So, I mean, this is just a nice slow, this is like a lawnmower engine or something.
Oh,
It's a nice slow motor. Alright, but the principle's the same regardless. Here's the challenge with this one. What is the formula or equation that we can write that's going to relate all the parts of this triangle? I drew the triangle bigger for you a little bit so we can see it better. On the right track. Law of cosines. I have all three sides, right?
yes.
I have all three sides and one angle. Since I only have one angle, I'm gonna need to use the law of cosines. Do you guys remember the law of cosines? Oh, you're
A squared plus D squared plus like I don't know.
minus 2ab cosine of c.
Yeah, that.
equals side c squared.
Yes.
And the important thing here, guys, is that the angle that you use has to be across from whatever you happen to call c. So what are we going to call c in this one?
7.
The 7. All right. So we have 7 squared equals 3 squared plus x squared minus 2 times 3 times x times cosine of theta. All right.
Theta is 400 pi.
Well, d theta dt is 400 pi.
You don't plug it in until you find the derivative of that.
That's right. We don't plug any of these other numbers. I'm not going to plug theta equals pi over 3 in. I'm not going to plug in the 400 pi until after I do the derivative.
Plug in 7 already because it's
Because 7 and 3 are constant. These are parts in the engine. They're not changing lengths. What's changing length is the distance between this little pivot point and where the arm connects to the piston, because the piston's moving back and forth. That's the only thing that's changing here is that x. Mm-hmm.
So for the why do you multiply with 2 pi for the for 200?
So let's go from here and actually simplify a little bit first, and then we'll do the derivative. All right. So we've got 49 equals 9 plus x squared minus 6x cosine theta. And now we're going to do the derivative with respect to t on both sides. Okay? Now, some of this is easy, and some of this we got to be real careful with, all right?
find the x and the t.
Yeah, that's our goal, is to find dx dt. So let's check this out.
0 plus 0 equals 0
Wait, why do you multiply
plus
both sides?
2x. Yeah.
0 plus 2x
Gx
Minus
dt
product.
dx dt minus 6 times, and then we got to do the product rule. You're right, Joey. So minus 6 times 1 cosine theta.
shouldn't be dx dt plus
Yeah, 1 dx dt times cosine theta plus
sine theta.
x times negative sine theta times d theta dt.
Why are you doing the theta dt again?
Because again, I have to do chain rule. Cosine of theta is negative sine theta d theta dt. Okay? Now, guys, one thing that you can help yourself out with is to go ahead and plug in what you know even before you simplify stuff. Okay? So, we know that x... Well, do we know x?
No.
We don't know x. Huh. But...
You know the
if we know theta, if we know this is 3, 7x, and we know that this is pi over 3, we can figure out x, right?
yeah.
Using the same formula, that law of cosines that we just had.
It's 60 degrees.
So 49 equals 9 plus x squared minus 6x times cosine of pi over 3. What's cosine of pi over 3?
It's
1/2.
1/2.
A half, okay? So this is 49 equals 9 plus x squared minus 3x. So I got quadratic to solve. X squared minus 3x minus 40.
It is 8 multiplied by 5.
Yeah, there you go, good. X minus 8 times x plus 5. You guys know how to solve quadratics.
It's 8 and negative
It's
5.
either 8 or negative 5.
8 or negative
It can't
5.
be negative 5 because it's not.
Considering
Can,
that it's 8
Yeah, it can't be negative because we're talking about the distance here.
plus it's hypotenuse, so it's
I love me some negative.
Yeah, and it's the length of a side of a triangle, so it can't be
I
negative.
love me some negative sides of triangles.
Okay? It's not too complicated, we got it, okay? So let's keep plugging in what we know, okay? Let's keep plugging in what we know. We have a 0, we have 2 times 8 times dx dt, which we don't know, we're trying to find that, minus 6 times dx dt
multiplied by 1/2
times the cosine of pi over 3, so that's the 1/2,
multiplied by
x we said was 8. What's the sine of pi over 3?
Negative 3, it's negative sign, so it's negative 3 over, root of 3 over 2.
Very good, root 3 over 2. And d theta dt we already know is
400 pi.
400 pi, okay? So guys, there's a lot here, but it's doable. Alright?
And you multiply it out.
So now it's just, this is simple algebra at this point, okay? 16 dx dt.
Look very simple.
Oh, you're fine.
Minus
Okay,
60.
minus 3 dx dt. I'm going to do a little simplifying along the way. And then let's see, we have 8 times 400 divided by 2. 8 times 200 is 1600 times 6 is 96 root 3 pi. Okay.
What? Wait.
Alright.
Hang on a sec. 200 times 8. 200 times 8 is 1600 times 6. Oh wait, I forgot 100 in there.
Yeah.
9600 root 3 pi.
That makes sense.
Yeah, sorry. Lost a couple zeros.
The speed you were doing that, I was so confused.
Oh wait, mistakes. Are you sure that's minus? Minus?
Oh yeah, 2 negatives, positive. There we go. Alright.
I'm still.
Wait, 3,000.
Come on, you guys can do the algebra. I'm just going quick.
No,
You guys can
I
do
think
the
it's not
algebra.
9,000. I think it's 1,600.
No.
It's negative 1,600. Root 3 pi.
You have 8 times 400, which is 3,200, divided by 2 is 1,600. 16 times 6 is 96.
Wait, where'd
So
you
it's
get
9,600.
6?
On the outside of the parentheses.
Oh, obviously. I forgot.
So. Alright, so at this point,
Simple algebra.
we've got dx dt, we've got a 13 dx dt. I'm going to take to the other side, so negative 13 dx dt equals the 9600 root 3 times pi.
You could divide by negative 13.
Okay, and then we just divide by negative 13, and we get dx dt is a negative whatever that equals. Someone with the calculator help us out, please.
What do you want me to do? So. 9, it's not 42.
4,000 what?
Simple algebra.
Negative 4,018.
Negative 4,018.
That
Okay,
doesn't make much sense.
and
That's like
No, wait,
exactly.
no.
Without pi.
that's a rate of change.
Oh, which,
That's a rate of change.
That's in radians?
What's our unit of measure? This is x, right? dx, what is x measured in?
Inches.
Inches. And what's our unit of time? Minutes. Okay. Do engines move really fast? Yeah. To spin around 200 times a minute, yeah, it's got to. It's got to be doing it over 3 times per second. So yeah, it makes sense that our dx dt would be really fast. And notice it's negative, so it happens to be moving away from the spark plug. It's getting smaller at the moment. So then an explosion must have just taken place and it's on its way back.
would we have to put on test 4,018 or negative 4,018?
Well, it asked for velocity, so that you'd put negative 4,018. Okay.
Simple algebra.
Okay, so this one's kind of a cool one. We're pumping up a balloon. We're blowing up a balloon. And this is one of those cases where we kind of have to make some assumptions. We're going to assume that this balloon was perfectly made, and as we blow it blows up as a perfect sphere. Okay? So we're going to suspend reality a little bit here and make that assumption. Alright, but we have this picture where we have the balloon getting pumped up, and evidently they don't have very good lung capacity because they had to use a pump. But we have air being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So I guess this is a pretty big balloon, so we won't hold it against them. They're using a pump. Alright,
Mr. Hicks,
yes.
aren't you probably air constant, shouldn't the radius change constantly, like in the same rate?
Well,
Because you're moving the same amount of air at the time?
it might be. We might find that when we do the formula, that well, what are we trying to find? The rate of change of the radius is,
DRDT.
that's dr dt. We may come up with a formula for dr dt that does not have r in it. And then, yeah, we would be recognizing, hey, it's not dependent on how big it is, it's going to be growing at a constant rate. Kind of like the ripples on the pond were.
Okay.
It didn't matter how big it was, the radius was growing the same rate. This one, we'll have to wait and see if that's the case. But what are we actually given? It says air is being pumped in at a rate of 4.5 cubic feet per minute.
Isn't dVdt because the volume increases?
Yeah, if we're pumping air in, we're increasing the volume. Okay, so that's dV dt, and this is 4.5 cubic feet per minute. Okay, the other thing that tips us off that it's dV dt is the fact that they gave us cubic feet, so there's a volume here. Okay, cubic feet per minute, and we're trying to find dr dt. Now, what's the formula that relates our volume to the radius with a sphere? Volume of a sphere, which is?
4/3 pi radius cubed.
It was on the PSAT?
SAT.
Oh, on the SAT?
Yeah.
V equals 4/3 pi r cubed. Okay?
Are we gonna have those formulas on the actual exam?
You don't get anything on the AP exam.
Really?
This is an IB. They don't give you all your formulas, you know? You actually have to memorize stuff. So, but
why IB having formulas?
Because we're advanced.
it's just their decision. So,
Because we're more
Do they
advanced.
give you all formulas? Or?
They're easier. Yeah,
they give you a lot, but
literally all.
I feel like
So-
in that type of class, the formula, like you still need to know how to, like, it doesn't really
yeah.
help you
Yeah.
that much.
Well, and here's one difference between AP and IB. AP, you learn a formula, and a lot of the times you're just using that formula. With IB, you may have a formula, but they're asking you to adapt that formula to a whole different situation. Not that we don't do any of that in AP, but they do. That's like the majority of what they do in IB. So it's a little different. So, anyways, let's go ahead and move on with this one here. We have here our formula. So now I need to take the derivative with respect to t. Okay, so if I'm taking the derivative with respect to t of both sides, derivative with respect to t. Okay, the left hand side ends up equaling dv dt, and the right hand side ends up being
4 pi r squared dr dt.
there we go, 4 pi r squared dr dt. Okay, 4 pi r squared dr dt.
So we found it?
Well, now we have everything that we need to find it, so we just gotta plug stuff in. Alright, does everyone see how we got to this though?
Yeah.
Okay, so now let's plug in the numbers we've got. We've got 4.5 for the dv dt. And we got 4 pi times the radius they said was going to be 2 feet. Okay, times, squared, dr dt. So we do 4.5 divided by 16 pi, dr dt, 4.5 divided by 16 pi. You could either leave pi in your answer, and in this case it would be a 9/32 pi if you got rid of the decimal. Or, better yet, just throw it in your calculator. What do you have? 0.88? That doesn't... I think you didn't put the parentheses around your 16 pi. 0.08?
0.0895246555.
Okay. Alright, so 0.0895, if we do 3 sig figs, what would our unit of measure be here?
Cubic feet per minute.
Not quite.
It
It is per minute.
It would just be feet per minute.
Because they're just looking at radius.
Yeah.
Yeah, it's the radius, right? And the radius is measured in feet. Okay?
Feet per minute.
So it's feet per minute. Our radius of this balloon is in feet per minute. And by the way, to point out, notice there is an R in our dVdt, so it isn't going to be a constant growth in our radius. It's going to be dependent on how big the radius of the balloon is at that moment. Okay, if we had taken the derivative and there was no R in there, then we would say, oh, it must be a constant. It must be growing constantly.
So it's
But-
not going.
It's not good.
In this case, it's not, yeah, because the R squared is in there, so it's going to be changing as the radius changes.
So is it like it grows slower as it gets bigger?
Yes, and if you think about it, that makes sense because you put the same amount of volume in, the bigger it gets,
Yeah.
it's got to fill more of that sphere, so the radius is going to grow a little bit slower the bigger it gets. You know, if you think about it, when you blow up a balloon, when you get the initial burst, it looks like it grows real fast, but then you keep blowing and blowing and blowing, and it's like just gradually getting bigger and bigger. Okay, so that's a fun one. I like that one.